Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The foundations of quantum mechanics, established in 1928 by John von Neumann, represents a pivotal contribution to the nascent field of quantum theory. This treatise, a towering achievement of mathematical physics, does more than simply systematize the probabilistic nature of quantum phenomena. It lays a rigorous mathematical foundation for understanding the theory's perplexing and counterintuitive aspects. This essay endeavors to undertake a meticulous, section-by-section examination, delving into the intricate workings of von Neumann's arguments, assessing the validity of his claims, and illustrating the enduring influence of his profound insights. It will undertake a close reading of the text, paying close attention to the internal structure, the logical connections, and the overall coherence of his exposition, all to provide a comprehensive and critical evaluation. Section 1. The Hilbert space formalism and the mathematical structure of quantum mechanics. Von Neumann commences by establishing the mathematical language within which quantum mechanics will be formulated. This initial section provides a rigorous introduction to the notion of Hilbert space. Hilbert space, as von Neumann presents it, becomes the arena in which the quantum mechanical universe is described. The key concept introduced here is that physical states are represented by vectors in a Hilbert space. These vectors, normalized to unity length, encapsulate all the information regarding a system's state. Von Neumann then explains the concept of linear operators, which represent physical observables. Observables, in this framework, are the measurable quantities of a physical system, such as position, momentum, or energy. These operators act on the state vectors, and their eigenvalues correspond to the possible measured values of the observable. The section carefully elucidates the properties of Hermitian operators, which are essential because their eigenvalues are real numbers, guaranteeing that measurements yield real, physically meaningful values. The spectral theorem, central to the framework, is explained. It allows for the decomposition of any Hermitian operator into a sum of projections onto its eigenvectors. This mathematical toolkit, foundational for all that follows, allows von Neumann to articulate the core postulates of quantum mechanics with a precision previously unattainable. The profound implications of this mathematical structure become immediately apparent from the way it links mathematics and physical reality. This rigorous formulation allows for a clear statement of the theory and provides the essential mathematical grounds for the theory of measurement. Section 2. The measurement problem. A rejection postulate, central to von Neumann's work, is the treatment of the measurement process, famously known as the measurement problem. The second section directly tackles this notoriously difficult aspect of quantum mechanics. Here, von Neumann differentiates between two distinct types of evolution. The first, the deterministic evolution, is governed by the time-dependent Schrödinger equation, which describes the continuous change in a system's state over time. This equation, a linear process, governs how quantum systems evolve when unobserved. The second type is the measurement process, which involves what he termed Process 1. Process 1 describes the instantaneous, irreversible collapse of the wave function when a measurement is performed. During measurement, a system's state, described by a superposition of various possible states, collapses into a single eigenstate corresponding to the measured value. This collapse, a discontinuous and irreducible process, fundamentally differs from the continuous evolution described by the Schrödinger equation. Von Neumann posits that the measurement act itself is inherently non-deterministic and introduces an element of irreducibility into the theory. This introduction of Process 1 is a bold attempt to account for how the probabilistic nature of quantum mechanics manifests itself during measurement. The projection postulate says that the wave function collapses from the superposition to an eigenstate of the measured operator. This explains why a single definite value results from measuring an observable. The implications are profound. The act of observation fundamentally alters the system's state, and it is this act that precipitates the transition from potentiality to actuality. Section 3. The statistical interpretation and the density matrix. Given the probabilistic nature of quantum mechanics, von Neumann introduces the concept of the density matrix as a tool to represent statistical ensembles of quantum systems. A system state can be the true superposition of states, it also be the statistical mixture of states. The density matrix formalism provides a mathematical framework for both types of situations. This section is crucial for understanding how quantum mechanics deals with situations where the exact state of a system is unknown, or where one is dealing with a statistical collection of systems. The density matrix, a Hermitian and positive semi-finite operator, allows for the calculation of expectation values of observables over the ensemble. The diagonal elements of the density matrix represent the probabilities of finding the system in a particular state. The introduction allows for a more complete description of quantum systems, incorporating both pure states described by wave functions and mixed states that represent statistical uncertainties. Von Neumann highlights the equivalence between the density matrix formulation and the Schrödinger equation when describing the evolution of a system. This section demonstrates how quantum mechanics, even with its probabilistic nature, maintains a consistent and complete description of physical systems. The careful attention to ensembles and statistical properties allows him to address the inherent uncertainty within the quantum world, providing a mathematical foundation for calculating probabilities and expectation values. Section 4. Quantum entanglement and correlations. The fourth section tackles the phenomenon of quantum entanglement, a consequence of the formalism that von Neumann lays out. This concept appears in modern physics, but it is implicit in his description of systems composed of multiple interacting particles. Entanglement describes the correlations between two or more quantum systems. These correlations exist even when the systems are spatially separated. Von Neumann's exposition does not offer any direct discussion of entanglement as a peculiar effect. Rather, it provides the mathematical machinery that makes entanglement both possible as a formalism and inevitable as a consequence. The key idea is that a system's state vector cannot be described fully by separate entities, but demands a unified description. When two or more particles interact, their wave functions become correlated, such that the measurement of one particle instantaneously influences the state of the other, regardless of the spatial separation. The mathematics provides the framework for calculating the probabilities of these correlated measurements. While von Neumann's presentation does not explicitly address the philosophical quandaries that entanglement raises, especially concerning locality and causality, the mathematical foundation he provides allows for systematic analysis. The work, in this section, describes the mathematics necessary for a complete and unified description of multipartite quantum states. Von Neumann's approach provides a framework for calculating the probabilities of measurement outcomes. Section 5. The problem of hidden variables. A significant portion of von Neumann's work addresses the question of whether quantum mechanics could be explained by an underlying theory relying on hidden variables. The idea is that quantum mechanics is incomplete, and that the apparent randomness and uncertainty arise from ignorance of some hidden parameters. Von Neumann presents an argument against the possibility of such theories. He demonstrates that any hidden variable theory must, by the consistency conditions of the formalism, violate the predictions of quantum mechanics. He proves that in such theories, the correlations between measurement outcomes would need to be different from those predicted by quantum mechanics. Von Neumann employs a rigorous mathematical argument to show that any hidden variable theory would be incompatible with central postulates, such as the superposition principle. This argument, if valid, has profound implications because it eliminates the possibility of a classical or deterministic foundation of quantum mechanics. His analysis is based on the structure of the states within the Hilbert space. He considers the expectation values of various observables. Von Neumann's argument hinges on the mathematical properties of the operators representing observables. The argument is carefully constructed, drawing conclusions based on the linearity of the expectation values. He shows that should hidden variables be present, then the expectation values would need to satisfy certain properties. These properties would need to be incompatible with the mathematical structures of quantum mechanics. The argument, for a time, played a significant role within the physics community, influencing the direction of theoretical investigations. Section 6: Extensions and Applications. This section addresses various extensions and applications of the formalism. Von Neumann considers the application of quantum mechanics to specific physical problems and shows how his framework yields results consistent with experimental observations. He discusses the harmonic oscillator, an example of a quantum system, and demonstrates how to solve the Schrödinger equation to determine the energy levels and wave functions for the system. He also addresses the concept of scattering theory, which explores the interactions between particles. He outlines the mathematical framework for describing how particles interact and scatter off each other. This section emphasizes the generality and power of the mathematical formulation. The framework can explain a wide range of physical phenomena. He considers the treatment of angular momentum in quantum mechanics and its crucial role in explaining the properties of atoms and molecules. This section provides examples of how the formalism can be employed in practical calculations and applications. Section 7: Re-evaluating the measurement problem. This section revisits the measurement problem. Von Neumann reflects on the implications of the projection postulate and its limitations. He does more than offer a rigid interpretation. He acknowledges the subtleties of the measurement process. He elaborates on the limitations of the concept of instantaneous wave function collapse and how it might apply to the measurement process. His discussion of the measurement problem is nuanced. The distinctions between the observed system, the measuring apparatus, and the observer become important. The question of how to demarcate the boundary between the quantum world and the classical world is raised. He argues that the act of measurement is inherently distinct from the continuous evolution of the system described by the Schrödinger equation. This distinction reveals the challenges in understanding the relationship between quantum mechanics and the classical world. Von Neumann's work doesn't provide a complete resolution to the measurement problem, but his analysis lays a clear framework for understanding its complexities. The section highlights the importance of further reflection and investigation to achieve a deeper understanding. Section 8: Concluding Remarks. The final section summarizes the key results of the book and reflects on their broader significance. Von Neumann emphasizes the importance of his mathematical framework as a foundation for quantum theory. He reiterates the significance of the Hilbert space formalism and the projection postulate. He addresses the implications of his work. The work provides a mathematical framework for the interpretation of quantum mechanics, as well as addressing the measurement problem. He reinforces concepts like the density, matrix, and the statistical interpretation. He discusses the limitations of the idea of hidden variables. The conclusion reflects on the broad scope and enduring relevance of his work. His work creates bridges to other areas of physics and mathematics. Von Neumann expresses confidence in the consistency and completeness of quantum mechanics. His work demonstrates an approach that can be applied to a variety of physical systems. In considering von Neumann's foundations of quantum mechanics, the impact on modern science becomes exceedingly clear. The systematic approach in describing the formalism provides a vital blueprint for understanding the theory. His construction of the Hilbert space framework is fundamental. The work presents a clear, efficient description of quantum mechanics. This presentation is important for a generation of physicists. The formulation of the measurement problem and the projection postulate are essential to understanding that process. The introduction of the density, Matrix is very important to understand the probabilistic nature of quantum mechanics. To understand ensembles of systems, the rigorous arguments regarding hidden variables are critical in the history of quantum theory. The clarity of his work becomes evident when contrasted with other approaches. The use of mathematics is especially important in all respects. The work becomes a masterpiece of scientific rigor. The enduring influence of von Neumann's work extends far beyond the immediate scientific community. The impact of his work is evident in the development of quantum computing and quantum information theory. Today, his mathematical framework remains foundational. Critics have addressed certain limitations, such as the lack of a fully satisfactory solution to the measurement problem. Nevertheless, his contributions have withstood tests for decades. His work has provided a guide for the development of physics. His clarity and precision continue to inspire research. His work is appreciated as a testament to the power of mathematical formalism. John von Neumann's Foundations of Quantum Mechanics remains a crucial contribution to the theory. It is an enduring achievement and a timeless work whose influence will remain for the foreseeable future.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.